So now that we've learned how to find the derivatives and just a few applications of the partial derivative, we're going to start taking a look at a little bit further into where we would ever use a partial derivative. And you might remember from Calculus 1 that one of the things that we could use the derivative for is to be able to find maximum minimum points. And that's what we're going to do in Calculus 3. We're going to use the partial derivatives to find maximum, minimum, and then a third type of point called a saddle point. Right? So let's go ahead and describe first of all the process to be able to find maximum and minimum points. Very similar to what you did in Calculus 1 is you're going to have to find some critical values, except in Calc 3 they're called critical points. Critical point is going to be an ordered pair that simultaneously satisfies this system. F sub x at a specific point equals 0 and f sub y at a specific point is equal to 0. Now, how do we determine if they're going to be maximum, minimum, or these saddle points? There's a formula that we can use. And once we find a point, we're going to plug each of those points back into this formula, D. Now, D is going to tell us whether it's a maximum, minimum, saddle, or if it's inconclusive. And so, if for some reason D is greater than 0, there's two options. It's either going to be a minimum if the second partial of x is going to be greater than 0. If the second partial of x is less than 0, you have a maximum. Now, if d is less than 0, then we have this thing called a saddle point. And I want you to notice on the trace of a saddle point, well, if you're coming from one direction, we have like this parabola that's kind of going on, then it's a maximum. However, if you're coming from another direction, you have a minimum. So this point right here in the middle is like a location to where in one direction it's a max, in the other direction it's a min. So we can just call it a saddle. Notice in the other diagrams we clearly have maximum or minimum values on these graphs. All right. So not every graph is going to have a max, not every graph is going to have a min, not every graph is going to have a saddle. It's up to us to be able to analytically find these. All right, so we're going to take a look at a few examples, and we're going to determine how to figure out max, min, and saddle. And then we can always look at the three-dimensional graph to verify our solution. All right, so let's get to it. We're going to start with a basic polynomial example. All right, we like polynomials because they're easy to work with. And we have this 3x squared y plus y cubed minus 3x squared minus 3y squared minus 2. Finding the partials to find the critical points. Fx, easy. 6xy minus 6x. All right, really easy partial. Fy, not as pretty as the first. 3x squared plus 3y squared minus 6y. And remember, we set those both equal to 0 because we want to figure out what, it's like a system basically. All right, now, how do we solve this? Well, we could use substitution, and we might be able to solve for y. But I think a little bit easier way to be able to solve this might be to take a look at the first equation, because this one's pretty easy to solve. Let's factor out an x. And if we do that, we're going to get 6y, or I'm sorry, we can factor out 6x. And if we factor out a 6x, that's going to leave us with y minus 1 equals 0. And so this is only true if x is 0 or if y is 1. Notice not and. Okay, so that's important. This is not one of the ordered pairs. It could be, but that doesn't mean it's going to be 0, 1 is one of the critical values. All right, what we have to do is we have to take 0, substitute it back into fy for x, and then we're also, in a different step, going to substitute 1 back in for y. We already know that these satisfy fx. Okay, so fx equals 0 when those two are true. Now let's substitute those back into fy and see when that's true. Okay, so fy when x equals 0 is going to be equal to 3 times 0 squared plus 3y squared minus 6y equals 0. We can factor that because now we only have a single variable. Let's factor out 3y, and that leaves us with y minus 2. And notice that the two solutions, y equals 0, y equals 2. And so thus, we have two critical points. X is 0, y is 0. So I'm going to make a little chart down here and just kind of keep a list of our critical values. So we have the point 0, 0. And then we also have the point 0, 2. Those are for when x is 0. We're going to do the exact same thing, but we're going to substitute y equals 1 into fy. So we're going to find fy when y is equal to 1. And if we do that, that just gives us 3x squared minus 3 times 1 squared minus 6 times 1 equals 0. This computes the, this should be a plus, sorry about that. This computes the negative 3. We can add 3 to both sides, so 3x squared is equal to 3, and hence x is going to be equal to plus or minus 1. Right? So we have two other critical points. We have 1, 1. Right? So remember, it says that when y is 1, x is 1. And then also we have the point negative 1, 1. So those are all of our critical points. Right? Now, how do we classify those? In other words, which one's a max, which one's a min, which one's a saddle? Are they all saddles? Are they all maxes, etc.? Well, remember we have to find our formula for D. And remember, D is equal to fxx times fyy minus fxy quantity square. All right, so let's find fxx, let's find fyy, let's find fxy, and then find a formula for D. Right, now, fxx, we already have the first partial, so we're just going to take this derivative with respect to x, so that's going to be 6y minus 6. Fyy, if we take the partial with respect to y of this animal, that's going to be equal to 6y minus 6 as well. All right. And then fxy, which should be equal to fyx, and we can verify that. fxy is going to be 6x, and then up here it's also equal to 6x if we do fyx. So that's a way to verify just to make sure you're on the right track. Right? So that's going to be equal to, I forgot what we said, 6x. And so our formula for D is going to be equal to fxx times fyy minus fxy squared. Okay? Or another way to write D is 6y minus 6 squared minus 36x squared. And again, remember, we need D to be able to classify those four critical values. All right? So now we're just going to go ahead and do that. So we have our critical point, and we're going to need a few things. All right? So we should definitely have the value of D, which remember we said was 6y minus 6 squared minus 36x squared. We also need the value of xxx possibly. All right, remember fxx was 6y minus 6. And then what we could do is we can classify the point. Okay? All right, so our first point. In fact, let's just write all of the points in here. So we have 0, 0. We had the point 0, 2. We had the point 1, 1. And we had the point negative 1, 1. Okay, those were all the criticals we got. Remember, way back up here, 0, 0, 0, 2, 1, 1, negative 1, 1. All right, so let's plug them in. If I substitute back in to the first term, this is going to be d is equal to, so we get 36 minus 0 squared. So that's 36. All right. Remember, if d is greater than 0, and it might be helpful for us to have these rules just because it's our first time. All right. Remember these rules that we have, and I'm just going to cut and paste these so we have them. If d is greater than 0, there's two options. Right, so I'm just going to paste it right here. So if d is greater than 0, then we have to rely on what the value of xxx or fxx is. Okay, so that's going to be 6 times 0 minus 6. And we don't even care what the value of that is. That's less than 0. So what type of point do we have? Well, d is greater than 0, fxx is less than 0, so we have a relative or local maximum. All right, we're going to finish this off, but right now I'm just classifying them underneath. 0, 2. All right, so d is going to be equal to 6 times 2, which is 12 minus 6. Minus 6 is 36 again. And then once again we plug in 0, so we get 36 again. All right. Now, what happens when we plug in to fyy? So that's going to be 6 times 2 minus 6, which is clearly greater than 0. We don't care about the value. So since d is bigger than 0 and fxx is bigger than 0, then this time we have a relative minimum. All right, so now we have a min. If we substitute 1, 1 in, if we substitute 1 back in for y, then we get 0 squared. We have 6 minus 6, minus 36 times 1 squared. That's just negative 36, which is less than 0. And we could stop right there because anytime d is less than 0, we have one of those mysterious saddle points. All right, so we just classify that as a saddle. And then mercifully our last one. This is probably going to be the same thing. If we substitute 1 back in for y, that gives us 0 squared. If we substitute negative 1 back in for x, that gives us negative 36 times 1, which is clearly less than 0. So again, these 2 points are saddle points. All right. And so finally, we know the classifications of these. All right. We could probably get the ordered triples if we wanted to by plugging them back into the original function. So let's just do that. So first of all, remember there was a max at 0, 0. So let's do this. So there's a max at f at 0, 0. And if you remember way back, our original function was this guy right here. I'm going to copy that so I don't have to. Right. And clearly if we plug in 0, 0, that's just going to be 2. All right, because all of this stuff is going to go to 0, and we just end up with 2 there. All right, so we can say that there's a max at the ordered triple 0, 0, 2. Remember, there was a min at the point 0, 2. Okay, so we're going to say there's a min at, now this one's a little bit sneakier, so that goes away, this goes away, so we have 8 plus 2 is 10, and then 10 minus 12 should be negative 2. All right, I'm going to check that one more time just because I don't feel like making another 16-minute video. So all the x's cancel out. 8 minus 12 plus 2. Yep, that's 10. Or, I'm sorry, negative 2. 10 minus 12. So there's a min at the ordered triple 0, 2, negative 2. Right? And then the saddle, actually 2 saddles, when f at plus minus 1 comma 1. All right. Fortunately, all the x's are squared. So we really only have to figure out one time. All right, so let me just punch that into the, well, this will be 3, this will be -3, so that cancels out. We get 1 plus 2, and then -3, so it should be 0. It should be that we have a saddle point right on the z-axis. All right, we'll check that out in a few moments. So we have saddle points at -1, 1, 0, and 1, 1, 0. And of course, the ultimate test to determine whether any of this works is to look at the graph. All right, so let me go ahead, and I had the graph saved somewhere. Yep, there it is. And I just did this one GeoGebra. All right, so here's our graph of our function. And I can't rotate this, but I think I got a pretty good version of what's going on with this. All right, so if you look at this picture, we have a maximum right here. And I know it's tough to see, but this is the point 0, 0, 2. Okay, and that is the point that we said that there was a max at. There was a minute 0, 2, -2. And notice if you go all the way down here, I know you can't see it too well, but if you graph it on GeoGebra, you might be able to see it really nicely. And then I want you to notice that there's a saddle point right here. There's another one that's kind of hidden, unfortunately, due to the graph. So what I would encourage you to do is to go into GeoGebra, graph the function, and then rotate it a little bit. I did it before I worked the problem, and indeed, GeoGebra showed that there were 4 critical values, 2 saddles, 1 max, and 1 min. All right, so we're going to take a look at 2 other examples that are non-polynomial, just to see whether or not this this relationship makes any, or this method makes any sense to anybody. So go ahead and watch the next 2 videos and try to work along with those.